Unit 6, Lesson 2, Applications of Similar Triangles. So let's look at some examples of applying similar triangles in some application problems. So here in example 1, the height of objects using shadows. Shiva is standing beside a lighthouse on a sunny day as shown. She measures the length of her shadow and the length of the shadow cast by the lighthouse. Shiva is 1.6 meters tall. How tall is the lighthouse? So what you can see here are pictures of Shiva and the lighthouse. And when the sun casts a shadow, it's going to cast a shadow at the same angle toward the ground. And that shadow can be measured in length. So you have 4.8 meters for Shiva and 75 meters for the lighthouse. So we can use proportions and scale factors inside similar triangles to determine the height of the lighthouse without actually measuring it, just by knowing the lengths of the shadows and how tall Shiva is. So you see here is two similar triangles. So we have one triangle here for Shiva and one triangle, that one here for the lighthouse. And you have two common angles, a 90-degree angle here and here. So those are corresponding angles. And the angle that the sun makes with the ground with any object at any time of day is going to be the same angle for both Shiva's shadow and the lighthouse's shadow. So with two corresponding angles, we know that the two triangles are similar. So what does this mean? Well, I can find the scale factor by dividing 75 over 4.8. And that scale factor will be the same scale factor as dividing the height of the lighthouse by Shiva's height, 1.6. And so this equating both ratios in my corresponding sides sets up an equation for me to solve where I have h as my unknown value. Now if I multiply both sides by 1.6, I can solve for h. So h would equal to 1.6 times 75 divided by 4.8. And the answer to that is 25. So the height of the lighthouse is 25 meters tall. Okay, let's look at example 2. A new bridge is going to be built across the river, but the width of the river cannot be measured directly. Surveyors set up posts at point A, B, C, D, and E. Then they took measurements relative to the posts. Use the surveyor's measurements to determine the width of the river. So the river, we're going to use these posts at point A, point B, point C, point D, and point E to help us determine the width of the river. And the width of the river is, I'm assuming, to be the distance from point A to point B. Okay, so the width of the river is the distance from A to B. Okay, so what we have here are two similar triangles, and if you don't see them, here they are. So for the triangle from A to B to C, and the triangle from CD to E. So triangle A, B, C is similar to triangle. And be careful here. C is going to be the common point there, right? And A and D are corresponding angles. So if I wrote A first, I'm going to write here D first, so D. And then it's going to be E and B have the same corresponding angles, so D, E, and then C. So D, A, B, C, triangle A, B, C is similar to triangle D, E, C. Okay, now I can find scale factors and calculate ratios. So let's call the width of the river x, and I'm going to end up finding that one. And let's set up my scale factor ratios here. So if I look at, let's look at AC, and the corresponding side is DC. So AC over DC. I'm doing the bigger triangle over the smaller triangle. And we also have DE and AB are corresponding sides. So AB over DE. And then the last pair of corresponding sides are BC and CE or EC. And the scale factors are all equal to each other. So let's plug in some numbers. So for AC, I have 50. For DC, I have 9. So 50 divided by 9 is equal to 5.5556, but I don't want the repeating decimal. So I'm just going to reduce this. You reduce it to lowest terms if you can, but if 50 divided by 9 is already the fraction in lowest terms, then you just have to leave it as 50 over 9. Now, AB over DE, well, that's going to be x over 13. And BC over EC is going to be, well, we don't have any of those measurements, so we're going to leave that one out for now. So we're going to equate these two ratios. So 50 over 9 is my scale factor, which is equal to the same scale factor as x over 13. So equating these two together gives me an equation that I can solve for x. And so if I multiply both sides by 13, I will have x equals 50 times 13 over 9. And the answer to that is 72.2. I'm just going to round that as well. So 72.2 meters. Okay, let's look at another example. Andrea is a landscape designer. She's working on a backyard that is in the shape of a right triangle. She needs to cover the yard with sod and then fence the yard. She starts by drawing a scale diagram using the scale 1 centimeters representing 6.25 meters. She marks the dimensions of the yard on her drawing as 5, 12, and 13 centimeters. A roll of sod covers 0.93 meters squared. How many rolls of sod does Andrea need? What length of fencing does she need? So I'm going to create a right triangle. Actually, let's use our tool here to make shapes. Here's a right triangle. I'm going to put the 90-degree angle there. And let's say this side is 5 centimeters, and this side is 12 centimeters. And the hypotenuse is the longest side, so it'll be 13 centimeters. Now, 1 centimeter equals 6.25 meters. That means my scale factor is going to be 6.25. So if I multiply all the lengths of this small triangle by 6.25, I'll get the equivalent triangle in meters. So the equivalent triangle in meters, so here we would have, so 5 times 6.25 is 31.25 meters. The 12 centimeter portion, when I multiply that by 6.25, is 75 meters. And the 13 centimeter portion, when I multiply that by 6.25, is 81.25 meters. Now I need to find the area of this triangle, because once I know the area, I can know how many sod covers I would need. So the area of my triangle is, remember, half the base times height, or base times height divided by 2. So in this scenario, 75 would be my base. The height is 31.25. I won't need the 81.25 to calculate this. So I'll do 75 times 31.25 divided by 2. And that gives me an area of 1,171.875. Now, if one sod covers 0.93 meters, so the number of sod covers would be, well, 1171.875 is the total area I have to cover. Each sod cover covers 0.93 meters squared. So if I divide that number by 0.93, I get 1,260 sod covers. That's how much I would need to cover this yard. Okay, so in summary, similar triangles, we can use them to help us find lengths that cannot be measured directly. It's just using the proportions of our similar triangles. And it's always going to be helpful to write your similarity statement and calculate your scale factor, and then equate that scale factor with the other corresponding sides. That's it, and that ends this video.